this computer. Okay, share screen, share. Go to this presentation. Okay, right. So let me, since this didn't get recorded, bear with me again for 5 more minutes for the sake of others. Okay, those who could not see it here. Okay. The previous video part segment itself, we have seen how it works for a while you are downsampling things. What we are right now seeing is while you expand things, right? This is what we would see here. So in this case, what has been done here is, let me go back to the slide which has just this. Okay, let me also erase this for a moment so that we could write afresh here. No, I don't. Oops. The eraser also not. Okay, eraser is there, which is not working. Although, okay. Okay, so those have been written earlier. I saved it, so it doesn't work. Obviously, okay. We will see here. See. Assume you want to upsample it. This is the pixels that were there as 1, 2, 3. While you want to upsample, you assume that in between the so you get 1 here, right? You assume a dummy pixel in between here. Okay, these two are the dummy pixels. So now these are the ones that you want to get after upsampling. So this is 1, 2, 3, 4 and 5. Now you look at in terms of even and odd pixels. Okay, let's first look at for example this even pixel. The weights we have figured out is 14641. So this middle one should get a weight of 6, this should get a weight of 4, this should get a weight of 4, and this dummy pixel should get a weight of 1, and of course there will be one more dummy pixel on the left hand side, assuming the padding or you consider other things. So now you retain only those where you have real pixels. So that's essentially this one and this one. Okay, each having a weight of 4 and 4, right? So 4, 4. Okay, that's your thing. So that means it's equal to 1 by 2. That's as far as the even pixel are concerned. Now you look at the odd pixel. You apply the same logic now. This which is there on the here should get okay, this at least I could erase here. Let me erase these values. Okay, let me now draw it again here. So this is okay. So this, for example, now what would happen? This would have a weight of 6 here, right? This have a 4, this have 4, this has 1, this has 1, this doesn't exist, this doesn't exist. So all that exists is 1 for this, and then in the middle 6, right? And after that there is 1, right? The whole sum is 8. Okay, then you divide it by 8, and that would give you 1 by 8, 3 by 4 and 1 by 8. You see here, this is 1 by 8 from here, 1 by 8, and this would give you 3 by 4. Those are the weights you use it to compute the intensity at the at an odd pixel. That is how you upsample things. Okay, is upsampling and downsampling clear? Again, this is an intuitive explanation only, because we already assumed here you have this mask of 14641. To get that, as I mentioned, you should assume a Gaussian distribution. You assume that this is a the filter is separable and symmetric. Okay, then you take, so you take, for example, the center pixel to be A, the next two to be B, and then next two on the left hand side C, right hand side second one C from the center. Okay, then for example, A plus 2B plus 2C, that's how you write it, make it into 1, and then separability condition also you impose it, and you would be arriving at finally this result. Okay, is upsampling, downsampling for construction of image pyramids, is that clear? I'll again share the paper with you so that you could go, for example, if you are interested in knowing exactly the derivation for this 14641. Okay. Yeah, is it clear? Any question?
Sir, why is upsampling necessary for this?
Right.
Like,
So you just hold on that question here. We will answer this in this wonderful diagram. Okay, this is again taken from the same paper. See, again, I could answer it with the earlier diagram also. Take a look here. Uh, See, this is something, for example, this is the image that is there xy at t plus 1. Okay, instant. This is there, which is the image on the left hand side is at the frame t. Okay, so you, for example, you apply optical flow here at the higher level, you got that value, and now the next you have to apply it at this level, correct? That means once you, whichever you got here as a result, you need to warp and bring it to the same scale as this. So that is when you need to upsample here. And again, this should be more clear. We haven't so far explained you the steps in detail. So this diagram, which we are now going to see, should clarify your doubt. That's so. This is your hierarchical Lucas-Kanade or the whole algorithm. Okay, this is again the it's grabbed from the paper itself. See, for example, what you do. This is your level 0 means the original image. This is the level 0 here. Okay, there are two images for you, I of t and I of t minus 1. What will you do now? You first apply here a Gaussian, you apply a low pass filtering. Okay, this is a low pass filtering you apply here, convolve with a Gaussian, that means, and then you do downsampling here, right? And that would give you the next level image here. You do to go to the next level in the image pyramid, you repeat this again. You again convolve with a Gaussian kernel, that's low pass filtering. You then downsample in the way once that 1 4 6 4 1, you do the downsampling here, and then you arrive at this next level. So you go on till the required level is reached. Okay, you exactly follow the same procedure for the other image also. I of t also you follow the same procedure. Okay, this is the motion estimation model here. So now what you do is you apply optical flow between these two images, right? That would give you the displacement field or the motion field here. That field, remember that it is on a, when compared to the level 1, the level 2 whatever you have is a downsampled version. So next what you will do, you would expand that. For example, if you had got there a 1 pixel motion, that's in fact equal to 2 pixel motion in the next level. And also now earlier, if that is a 100 by 100 image, in the next level when you come, it should be a 200 by 200 image. So you do two things here. First thing, expand, which is nothing but upsample your image, followed by the displacements. In fact, what are shown there are now has to be multiplied by 2, because 1 pixel motion there is equivalent to the 2 pixel motion. You do that now, right? This is your motion field. So this warping you apply to this pixel. This W means warping here. Okay, the other image at level 1, you apply this warping here. So this is the warped image of which is there at level 1, and now you apply Lucas-Kanade method, this warped image, and the other image teeth frame image, you apply the motion field here. Again you repeat the same procedure. Now you apply the you from Lucas and Kanade method, you compute the displacement vector, you expand it, or in other words upsample it, then you multiply those values by 2, right? And then with that value, of course the other field also would come there. With that you warp it now. So the earlier motion plus this motion, the whole which you got, with that value, the image which is there at level 0, you warp it, then you get this image. Then you apply Lucas and Kanade method between these two, and so on. Is that clear?
So what does warping mean here?
Warping is applying transform. So we have seen in image transform, if you recollect the last two slides, how you do inverse warping also, there we were discussing. This is
Okay,
essentially equivalent to, you know, see the image which you get after at the end of this, okay, what it tells you is at each pixel how much motion it has in x as well as y. Okay, that's the displacement vector. Applying it to this image is referred to as warping. So there, if you recollect, we mentioned that you in fact won't be applying it right away. You find out an inverse displacement field, and then you do a warping based on that to avoid any missing areas there are any holes, because the way that transform could go. Is it clear?
Sir, so we will check the eigenvalues of the second order matrix at each level, and if the eigenvalues are high, then we will choose that level and then warp it back. And
no, why eigenvalues here? Yeah, see,
that
you don't really eigenvalues. This you make an assumption on how much should be the displacement field, and then with that you decide a priori with whatever knowledge you have. You decide a priori and go ahead with it.
So like once you obtain the displacement field, then we expand it. Till that it's clear, and even multiplication with two part is clear. But after this, like, what do we do after we have expanded it? And
right. See, now what you do is you don't take the original image, but you apply the, see, you want to, so that means once you apply this displacement field, for example, you got a displacement field here, okay? Once you apply this displacement field, you are bringing it much closer to this image, isn't it? Then your displacement earlier, your displacement might be 10, right? Now, after you come to the next level, because if you adjust this, it comes closer here now. So instead of, you are compensating for the displacement right now, and then you're doing it so that it is now the displacement you could expect is of few pixels or subpixel only.
so by applying the displacement field to the level 1, we're actually like transforming the image to like closer to level 2.
Exactly.
Sorry, closer to the other side.
Exactly, that's right. So now with that resultant image, you do optical flow. See, the problem why we are all doing it is the displacement is too high to fit into few pixels. So you are first doing a very gross estimate, and from that gross estimate you are adjusting and bringing them to the closest level possible. And then at that level, now once you apply this transformation, it is now only few pixels at this level. So you, that way you go one step next. Is that clear?
Yes.
Sir, so after getting to the final level, we should form that second order matrix, right, to find u and v for each pixel.
Yeah, that's a good point actually. See, what is that metric is telling you is in fact that anyway to solve it you have to do it at every pixel at each level actually. See, that metrics will come as long as there is an optical flow, isn't it? With Lucas and Kanade, you are going to apply at each level, that metrics will come here, here, here. So that all that metrics tells you is whether you have a good inverse or not. In other words, is that a reliable transformation or not? This you would in fact be doing at every stage.
Sir, so how will we know at which level we have to stop?
See, you go till, see, that is what, for example, you should be having some prior knowledge about how many pixels movement can you expect, okay? So that until and unless this goes to a subpixel level, so suppose if you know that the maximum displacement to expect is 10 pixels, okay? So if I subsample it by 2, it will go to 5. If I subsample it by 2, it will go to 2.5, further 1.25, further 0.625, correct? So I reduce that. So to this level, I start my Lucas and Kanade at this level. And then from here, I come here, then I come here, then I come here, then I come here, right? So this would be level 0. This would be level 1, level 2, level 3, level 4. So in this goes, if I know the a priori that there, if I what I expect is 10 pixels displacement, then I will use 4 level Lucas and Kanade. That's all.
So the size of the image will be different at each levels, right?
Yes, that's right. So size of the, and that is helping us to bring the actual displacement. So 1 pixel displacement is different at each level when you see compare it with the L0 image. See, for example, if here I get 1 pixel displacement, that's equal to, is different. It's in fact equal to 10 pixel displacement here, right? So that is different here, but here, yeah, that's right.
Sir, and then how will we bring this L4 to the original size again then?
Yeah, that's exactly what we are doing here, right? That's what the upsampling and downsampling, we are gradually moving towards this level 0, right? You are at level 2 here in the beginning, correct? You did the whole thing, you got the warping. This is where you are upsampling your image, and then you multiplied it by 2, you applied this warping here, and at the end of it, you are in the, already by the time you did it, you are in the level 1 here, correct? So then you repeat the whole process. By the time you reach here, you are at the level 0. So in other words, upsampling is gradually bringing you upsampling your displacement fields, and then applying that is gradually bringing you to the final level.
Sir,
yes.
Why do we add the UE values found from level 2 with the UE values found in level 1 and do it accordingly?
Right.
For,
Can anyone answer this question? That's a good point.
In the higher levels, we obtain coarser movement, and in the lower levels, we obtain finer movement. So finally, we have to add them all up to get the overall motion.
That's all. Because every time you are going to warp that image which is there afresh, you are applying it. So you need to combine everything put together, and then you apply it here. That's correct. Good. Is that clear, Mohammed?
okay, sir.
Yeah. Any other question here?
Sir, by warping, the image has moved a little bit, no, sir?
Which way?
Along the UV direction.
Yeah. See, that's actually see, ideally, yeah, for a see, if it is an M by N image, it will still remain that it is just to show it symbolically. They made it as if it is moving here, I guess, in the image. Otherwise, the image boundaries will be, of course, where that object shape could change. See, if that is an object undergoing some deformations, that's where that object could go. But again, that's the best, I think. Yeah, this image is not so great image to discuss, but I don't have a better image. This you could think as if it is undergoing some deformation. That's all they want to mention it here.
The variations will be very small, so it's not observable.
Right. That's right. Okay. Yeah, the same thing has been mentioned here as an algorithm. This you please go through it yourself. I skip this out, but would rather spend a few more minutes on looking at the results here, what it is exactly. Okay, so this is without Lucas and Kanade. Of course, it fails, but rather, yeah, 1 minute. Oops. This is only better. Okay, so this anyway is expected. This fails badly here. Okay, for example, this all is going very crazily here, right? This also is going, yeah, of course it fails, but this would be more interesting stuff. Now they have applied Lucas and Kanade here. Now I have few questions for you here. This thing, for example, they were doing analysis in this region here. Okay, if you take a look at here, they are showing whatever displacements they have as vectors, and Sorry. So you see only displacements in the x direction. Can you tell me why? The first question is, your vectors are almost horizontal. Sorry. The vectors are almost horizontal. The obvious reason could be?
Sir, aperture problem.
Sir, wind direction.
No. By the way, how do you think that
Sir,
they
we
have?
got the gradient. The
No.
gradient
How
is.
do you think these images are acquired? That should answer the question. So if you remember this GIF image I was showing you, one will be this and slightly moved there. So essentially they were moving the camera, okay, and then capturing the results there. So perhaps what would have happened is they might have moved the camera this way, not anything in the y direction, okay. So that would give you only the displacements in the x direction. Does that make sense?
Yes, sir.
Okay, good. Next question for you is, in these regions, you would see large displacement fields in the x direction than in these regions. Can you tell me why?
There's a gradient over the gradient value in this region is
No.
comparatively high, like closer to the edges, you can see.
Sorry?
Sir, can you repeat the question, sir?
Look at the displacements here in the background. Those are smaller compared to the displacements you have here. Can you tell me why?
Due to parallax, the tree is much closer to the camera, so it moves farther or
Very
faster.
good. That's right. That's right. See, this is the effect of you have a tree and the background is far. Okay. So that's why your camera is closer to the tree. So that's why when you are moving this camera, the displacement that you would find out there would be much higher than the displacement of the pixels which are there in the background. This is all 3D to 2D conversion is there here. So that's the reason why here you have a lot of displacement fields. Okay. And the next question for you is this region. Yeah, I hope I could try it. Okay. This region, there are some issues. What is it that might be contributing to these issues? What are the factors that might be contributing to the issues there as far as the displacement field is concerned?
So there we are finding like corresponding to an edge. So so it doesn't exactly knows the next point where it should map to.
Sorry?
Sir, like these points, since we only know the smoothness constraint, we know the component which is perpendicular to the gradient, right?
Not really that. There is one more reason here. There is another reason here.
Sir, the neighboring pixels are. Sir, there aren't much neighboring pixels along the edges when compared to the pixels in the tree trunk.
Yeah, maybe you are. What you mean is the answer probably is like it is because of the occlusion that's happening. See, when you are moving the camera in one place, what would happen is the information which is there in one image versus the another image, the occlusion comes because of the view angle of your camera. So once the pixels are occluded, there is an issue with that. So that's one thing that contributes. Another thing perhaps, which I'm not very sure, also could contribute is you pretend here that, that anyway the motion wise also you could say, for example, you pretend as if all pixels in your neighborhood move with the same displacement field, but
that was our assumption first.
Corresponds to that which is there closer, and the other part which is farther, which is having a different velocities. So that might be also screwing up things a bit there. Okay, these two could be the potential reasons for that. Are those reasons clear?
So what is occlusion?
Occlusion is you are able to see one frame whichever you could see. The moment you are moving camera slightly in a different position, you are keeping it, those parts are occluded in the other image, you can't see it. See, suppose there are two people standing, the moment you are moving camera into a slightly angle, it might occlude, okay, or hinder something which is there earlier visible might not be visible. See, this is like this hand would now occlude it, the backside of my hand, but the moment I move it here, you could see it. So this is occlusion. So similarly, when you are moving camera, some information which is visible in one frame is not exactly visible in the other, and vice versa. That's occlusion. So essentially, then you are trying to find out transforms between these two where the information is not exactly consistent between two frames, and that's causing you problem. Is that clear?
Yes.
Okay, good. So I think with this we are done. Okay, we are done with. We will stop with this optical flow. Yeah. Again, with just few points to add here. This is something there in the 1980s. The method is there. So are you not wondering, is this still the state of the art that you would be using, or could there be something else? Yeah, still you use it, but you these days you won't use it alone. See, one kind of things that they would be using is, for example, there is another class of methods which we're not discussing now, that's called as a sparse Lucas-Kanade method. Okay, this what they do is they won't do it at every pixel, but as we discussed earlier, this is reliable only when at those pixels which have second order movement value being very good, right? This our second order movement eigenvectors are large and similar values. So they pick those points, and at those point, around those points, they apply Lucas-Kanade method rather than applying at the whole points. That's one thing they do it. And then there are other things like motion models we discussed earlier. So for example, this is, so if you recollect, we divided the whole motion like introduction to motion estimation. One we mentioned is the feature based methods, right? The feature based methods, and then dense methods. These are the two classifications. People, what would they do is they in fact use them a combination of both. So for example, in feature based methods, as I mentioned, at some points they would use Lucas-Kanade. Okay, the other points they could use let's say find out key points there and estimate their motion, and from that first estimate the global motion at the first level, and after they compensated for large motions using the feature based approaches, then they come back for finding out a finer variations. They will come back to these Lucas-Kanade, and then maybe other variants of slight variants of Lucas-Kanade also. So it's a other level of hierarchical approach, okay, where you would use it. And again, even in motion models also, again you would find out literature where for finding out features. Of course, if you are using shift or scale invariant Harris transform, that already takes care of looking at things at the different scales. But there are other global methods also where they approach this problem in a hierarchical way. And then another thing you might have noticed, there is, we are not looking at what are the regions that are coherently moving. So that's something we have not discussed so far. So there are again methods that look into first to figure out objects that are coherently moving in the image, and within that, for the whole object, then they might do a feature based thing. Okay, there are those kinds of variants of methods are also there. And then they might look at also the gradient information also they look at, and sometimes they also look at region based characteristics to find out the motion. Okay, for example, some textural information in a given region might give you some statistical metrics that are consistent for that region to find out in the other region. So there are works which use that. So you would find out literature these days where you won't use just a single method. You use a combination of feature based methods, dense based methods. They are like stitched together, combined together in a clever way, and again they are customized with respect to the specific application that they need to handle with. So those are the kind of literature that you would see here. Okay. Is that clear? Okay, so we can stop here. So by the way, it has been quite some time giving you any assignments. I would post, very likely in the next couple of days, I'll give you an assignment. And if you remember, there is a technical paper presentation part is there as a part of this computer vision. So what I am thinking of is you pick one paper which has this background and relevance to this, and then something which we have not discussed in the class. Okay, then you make your own video and then post the video. That's what I'll go through it, and then everybody could then go through them, and then that's how we could assess the presentation of it. So each one could do one. Anyways, it doesn't require any sophisticated things. You could do it. For example, I'm sure almost all of you should be having PowerPoint. You might be having. So even you could make a presentation, and then in PowerPoint you could record your PowerPoint there itself. It gives you an option. So you simply record it, and then it's up to you. That's the basic thing. Then you could actually do a YouTube video, a proper YouTube video, where just like this Zoom session which you are looking, where you could write it there. Or I leave it to you. But given that everybody is having this PowerPoint, you should be able to record it there. That's the least case you could think of. For that also, what I will do is, what is recommended or encouraged is that you come up with your own, you go through again. You will now, with the VPN connection, you will be able to connect to all these IEEE journals, right? And if you go through my first presentation, you have the list of journals and conferences, important journals and conferences. You pick something which we have not fully covered in the class, but has relevance to it, an extension of that, and you study it and give a presentation on it. And you post your video there, okay, on your YouTube. Again, that size also should not matter much, because 30 minutes usually should not be more than 400 MB, or in the worst case, it should be 500 MB, not more than that. So should be able to upload it and then share it. Does that make sense? I will post some topics, so those who could not figure out topics on their own could see them, and if they think that would be interesting, you could pick that and make a presentation on that. I will share some of those topics very soon. Yeah.
Regarding the assignment, it seems that MATLAB won't work at our homes. It only works on college servers. So how do we
nowadays? Okay, let me stop this. Probably this I will stop the recording part here. Just 1 minute.